Welcome back to the Deep Dive, the place where we sift through the sources so you don't have to, turning mountains of data into focused, actionable knowledge.
Today, we are looking at something huge. A fundamental rewiring of the entire global computing infrastructure.
It's not just an upgrade, is it? It's a completely different way of thinking.
Exactly. We're seeing this explosion of connected intelligence that has moved far, far beyond the centralized cloud that we've all gotten used to.
We're all living in this world that's just defined by a sheer, almost overwhelming volume of data being generated.
Overwhelming is the right word. And critically, this is forcing an inevitable shift of artificial intelligence away from those massive data centers and, directly into the devices in your pocket, your car, and on your factory floor.
That dynamic is the perfect foundation for our deep dive today. The core focus is this aggressive convergence of three massive forces: artificial intelligence,
Right, AI.
the Internet of Things, or IoT,
Mhm.
and the result of those two meeting, which is this decentralized field we call edge computing.
And that convergence, it's totally redefining how, where, and I think most importantly, why computation happens at all.
It's like the difference between sending a letter to headquarters and having a conversation right there in the room.
That's a great analogy. Our mission for this deep dive is to take a really comprehensive look at the hard statistics that are defining this transformation, specifically focusing on the 2025 landscape.
And we're going to examine the revolutionary new hardware that's powering this shift. We're talking about the specialized silicon.
We are. Then we'll explore how industries are leveraging this localized intelligence right now, and finally look ahead at the future connectivity paradigm, which is 6G.
Along with, of course, the deep security and governance challenges that come with creating this fully decentralized global brain.
It's a massive topic.
It is. And we got some fascinating material guiding us. We're drawing on the most recent market forecasts for IoT and AI adoption, some really deep analysis of the edge AI accelerator market, and comprehensive technical reviews of upcoming silicon from the giants.
We're talking Apple, Intel, NVIDIA, MediaTek, all the big players.
Plus, we've got the cutting-edge research on 6G and this, frankly, paradigm-shifting concept of semantic communications, which we'll get into.
So this is a deep dive into the engineering, the economics, and the ethics, the governance of how distributed intelligence is being built, secured, and connected at a scale we've never even imagined before.
Okay, let's unpack this with some foundational figures that truly frame the magnitude of this shift. We have to start with the AI market itself, which is it's experiencing colossal and sustained growth.
It really is. The data we're looking at shows the global AI market is forecasted to reach, get this, $407 billion in 2025.
$407 billion. That's not just a headline number, is it? There's a story behind that growth.
There is. That figure represents a massive 23% compound annual growth rate, a CAGR, starting from 2023.
So a nearly 25% growth year over year, sustained.
Sustained. That kind of double-digit growth tells us something really important. AI has moved past the pure hype cycle and is now, firmly in the execution and integration phase across the entire industry.
So companies aren't just experimenting with this stuff in a lab anymore.
Not at all. They are deploying. And deployment at scale requires specialized, robust infrastructure, which is exactly why we're here talking about the edge. It's the how behind the what.
And the long-term economic impact is even more staggering. I mean, this number gives us the why behind all this investment. AI is expected to contribute a massive $15.7 trillion to the global economy by 2030.
15.7 trillion. It's almost an unfathomable number. But the key thing to understand is where that value actually comes from. Our sources show that over 50% of that impact,
Over half of it.
over half, is projected to come directly from productivity gains.
So not necessarily brand new sci-fi industries, but making what we already do much, much better.
Precisely. We're not just talking about entirely new industries being created from scratch, though, that will happen too. We're talking about fundamental, efficiency-driven changes to existing work.
Give me an example.
Okay, think of manufacturing logistics. AI can optimize a global supply chain to reduce transit time by just 10%. That alone is trillions of dollars in accumulated savings over time.
Right.
Or look at financial services. Predictive fraud detection moves from something that's reactive, analyzing what already happened, to real-time intervention. It stops the fraud before the money is even gone.
These productivity gains just generate immense economic value by lowering costs and speeding up processes across, Well, every sector.
Virtually every single one. And the adoption momentum we're seeing confirms that this isn't some niche technology anymore.
Not at all. As of the second quarter of 2025, a full 95% of Fortune 500 companies report using AI in some capacity.
95%. It's table stakes now.
It is. And globally, AI is projected to power 80% of all digital transformation initiatives. So when nearly every major company is betting their future on a technology, you know that the demand for instantaneous computational resources is going to just skyrocket.
And that intense demand leads us directly to the source of the data that fuels this engine.
The Internet of Things.
The IoT device tsunami. It's the perfect term for it. If AI is the brain and the processing power, then IoT devices are the nerve endings, constantly sensing, capturing, and feeding data into the system everywhere, all the time.
Let's put some numbers on that proliferation. Now, we should be clear, these estimates always vary a bit depending on how you define a connected device.
Of course. Is it just your phone and laptop, or is it every tiny temperature sensor in a smart building? It's a big range.
But the more realistic and, I think, reliable industry consensus forecasts that there will be approximately 27.1 billion connected devices globally in 2025.
27.1 billion. Let's just pause on that. To put that number into perspective, that's approaching 3 connected devices for every single person on the planet.
Wow.
And this ratio, it fundamentally redefines our concept of infrastructure ownership. It's no longer about a few massive mainframes in a data center. It's about billions of tiny distributed decision makers.
And that proliferation is absolutely not slowing down. This device number is expected to cross the 40 billion mark globally by 2030. Or maybe 2034.
We are accelerating toward a future where we have this dense, interconnected digital web covering the entire planet.
So, okay, let's connect the dots here.
Right.
We have AI growing into nearly $500 billion market.
Right.
And tens of billions of devices feeding it petabytes of data every single week. This is where we get to the core question. Why does this explosion necessitate a shift away from purely centralized cloud computing? Why can't the infrastructure we already built just handle it?
That is the key question. We built the cloud paradigm around this idea of centralized efficiency. But now it seems that very centralization is becoming the bottleneck.
It's a victim of its own success.
In a way, yes. It's simple physics and economics creating that bottleneck. Cloud computing, relying on these massive centralized data centers simply cannot handle this volume and, crucially, the speed requirement alone.
It's the round trip, isn't it?
It's the round trip. When you have billions of devices moving every single byte of raw high-resolution data back and forth to a remote server for processing, introduces prohibitive latency and just unsustainable bandwidth costs.
Let's make that concrete with the autonomous vehicle example. What is the actual time difference between an edge decision and a cloud decision?
Okay, it's the difference between an instantaneous reaction and a potentially fatal one. Edge AI can deliver what's called inference in single-digit milliseconds, let's say 5 to 10 milliseconds.
Practically instant.
For human perception, yes. Now, a cloud round trip, which involves sending the data up to a satellite or a fiber point, processing it, and getting the result back down, that often introduces delays of 100 milliseconds or more, even on a good 5G connection.
A tenth of a second. Doesn't sound like much, but...
But if an autonomous vehicle needs to identify an unexpected pedestrian and initiate braking, a process that happens thousands of times a second, that 100 millisecond delay means the car travels several feet further before the command is even executed. High-stakes data absolutely requires local processing.
That makes it very clear. The data explosion necessitates a decentralized approach.
It's a physical requirement.
And that spatial breakdown of where the money is, the revenue is interesting too. While North America currently holds the largest market share for AI revenue, about 41% globally.
Which makes sense. They pioneered the cloud model.
Right. But the fastest growth is clearly happening elsewhere.
That's right. The Asia-Pacific region is the fastest growing market. It's projected to hit a significant $105 billion in market value by the end of 2025.
And why is that?
It reflects the rapid digital transformation happening there, particularly in manufacturing and smart city infrastructure. They're not retrofitting old systems. They are building new infrastructure based on edge principles from the ground up, which just accelerates adoption massively.
Before we move on to really defining the edge, I want to highlight one truly surprising industry adoption leap from the source material. You'd expect manufacturing and consumer tech to lead the AI charge.
And they do.
But our sources point out a dramatic, almost shocking increase in the legal field.
It's a staggering transformation. The legal field has seen a 300% increase in AI usage just from 2023 to 2025.
300% in 2 years.
In 2 years. And this isn't about replacing lawyers, it's about replacing the drudgery with hyper-efficiency.
So what does that actually look like?
Okay, take complex litigation or a big merger and acquisition. Contract analysis used to require hundreds, maybe thousands of paralegal hours to review millions of documents for specific clauses or patterns. It was a huge cost center.
And AI changes the economics of that completely.
Completely. AI-powered contract analysis tools can process that same volume of documents in minutes, instantly flagging relevant clauses and risk exposure. This shift fundamentally changes how legal services are priced and delivered.
It creates massive disruption.
Not just in efficiency, but in accessibility and cost reduction for the client. It really just underscores that AI is no longer optional. It's a necessary tool for productivity, even in the most traditional, paper-intensive sectors.
Okay, this is where it gets really interesting for me. Defining the actual difference between where AI used to live, the cloud, and where it's moving the edge. Let's start by defining those two poles clearly for everyone listening.
Right. So traditionally, we've all relied on what's called cloud AI. This meant heavy computing, large language model training, massive scale data analysis, all typically run on powerful remote servers in these huge data centers.
So think of sending every photo you take to Google Photos for processing, or relying on Amazon Web Services.
Exactly. And the key trade-offs there are pretty clear. You have a full dependency on a stable, high-speed internet connection. You have potential delays because of that transmission time we talked about. And of course, the inevitable privacy risk that comes from transferring your data externally to a third party.
And then you have the alternative, on-device AI or edge AI.
Which means the processing happens directly on the local device, the smartphone, the smartwatch, the chip in a factory machine, or the car's dedicated processor.
The classic and I think most effective example is Apple's Face ID.
It's a perfect example. It delivers instant results precisely because the recognition models run entirely inside the device's chip. It never sends your facial geometry data off the phone itself.
But crucially, the future isn't this binary choice, is it? It's not one or the other.
Not at all. As our devices get smarter and connectivity improves, a hybrid future is emerging as the dominant standard. It's all about balancing the speed of the edge with the scale and training power of the cloud.
And Gartner has a prediction that really crystallizes this. They say 3 out of 4 AI interactions are predicted to occur on devices rather than solely in the cloud by 2026.
That's a massive tilt toward decentralization in a very short amount of time.
So what are the mechanics of this hybrid model? How does a device decide what to do locally versus what to send away?
It's about dividing the workload based on speed and resource needs. So the edge manages all the immediate latency-sensitive tasks. Think voice commands, initial image recognition, predictive text on your phone. It uses smaller, highly optimized models for those.
And the cloud handles the heavy lifting.
The cloud handles the resource-heavy jobs. So training the next generation of that large model, complex system-wide coordination between thousands of devices, and of course bulk data storage for those multi-petabyte data sets.
We see this already in things like Microsoft's Copilot plus PCs or Google's Pixel phones.
We do. They use dedicated local AI cores, or NPUs, for all those real-time functions, but they still sync with cloud servers for extended learning and to receive major model updates. It's the best of both worlds.
So if this is the direction of travel, let's really drill down on why decentralizing AI is so essential right now. Beyond just the volume of data, let's focus on the benefits for you, the end user. Our sources often group them into what we can call the core BLURP factors.
Bandwidth, latency, energy reliability, and privacy.
Let's start with latency, because for physical systems, it's just a non-negotiable requirement.
It is. Edge inference eliminates that cloud round trip, which means you avoid the high-stakes delay caused by sending data over long distances. As we discussed with the car, for critical applications like a robotic arm needing to adjust its grip or an ice detection alert on a remote wind turbine, that immediate real-time response is mandatory.
Any delay over, a few milliseconds can undermine the whole system?
Any delay over 10 to 20 milliseconds can undermine the efficacy or even the safety of the system.
Okay, then there's the absolutely crucial factor of privacy and security. This seems like maybe the biggest selling point for the edge, especially in consumer devices and regulated industries.
It's a massive driver, and it's essential for compliance. Keeping sensitive data like patient health records governed by IPA or consumer financial transactions protected by GDPR local ensures that these organizations can comply with really stringent data regulations.
Because the data never leaves the device, or at least the local network perimeter.
Exactly. When the data never leaves, the risk of external data transfer and a breach is minimized. This principle is driving the rapid adoption of things like federated learning, which we'll get to later, where models are trained on distributed, localized data without ever centralizing the raw, sensitive information.
Finally, we hit bandwidth and energy efficiency. I mean, if every one of those 27 billion devices was constantly streaming raw, high-res video to the cloud,
The internet would break. The bandwidth and energy demands would be unsustainable and just astronomical. It's not feasible.
so how does edge processing provide leverage here?
It's huge. It allows the device to process all that raw data locally and send only the smallest, most important, actionable insights.
So instead of a video feed,
Right. Instead of streaming hours of gigabyte-heavy high-resolution video feed, the device just sends a tiny message packet that says, fire detected at coordinates XY.
that's a massive reduction in data.
It's a drastic reduction in bandwidth consumption, which also saves substantial energy. And that is absolutely crucial for the millions of battery-powered IoT devices and wearables whose entire lifespan is determined by how little data they have to transmit.
This necessary shift is obviously creating an enormous new investment opportunity. Our sources project the edge AI market to reach a massive $163 billion by 2033.
That's growing from just $19 billion in 2023. It's a 24.1% CAGR. That's where the smart money is moving.
That growth is vast, but we have to provide a bit of a reality check here. We need to acknowledge the key restraints and challenges involved in actually deploying edge AI. It's not easy.
It's not. The first and maybe biggest obstacle is the substantial initial investment required for the specialized hardware and the development tools. This isn't cheap.
And that's where the talent gap comes in. I mean, if the market is projected to reach $163 billion, how can we trust that projection if the industry doesn't have the skilled workers to actually build and integrate this stuff?
That's a critical point. Compounding the investment cost is a significant scarcity of skilled professionals. There's a real talent gap for people who understand both the intricacies of AI modeling and the severe constraints of edge hardware.
It's a cross-disciplinary skill set.
It really is.
Yeah.
Deploying AI at the edge requires expertise in data science, embedded systems, and industrial networking. That combination is in extremely high demand and very short supply.
And then there are the physical constraints on the ground. It's one thing to run a large language model in a temperature-controlled data center with massive cooling systems.
It's another thing entirely to run it in a tiny, dusty sensor on a factory floor that might be subject to extreme heat or vibration. The integration complexity is huge, particularly for businesses trying to retrofit edge AI into their existing legacy IT infrastructure.
And the physics problem.
The physics problem is paramount. When you condense powerful AI processors into small, often fanless devices, power and heat management are major issues. These chips generate concentrated heat loads.
And if you can't get that heat out,
If that heat isn't efficiently dissipated, the system automatically slows itself down. It's a process called thermal throttling. And that causes the very performance loss you were trying to avoid in the first place, or it just leads to premature device wear and failure. Careful engineering and new silicon architectures are mandatory to overcome this.
that challenge of physical constraints, specifically power and heat, brings us perfectly to the hardware. On-device intelligence requires specialized muscle. We're moving away from the dominance of general computing chips toward these specialized accelerators.
Right. The processor landscape is shifting, but I call it an evolution, not an instantaneous revolution. Even in 2024, the central processing unit, the traditional CPU, still held a dominant market position in the edge AI accelerator market,
What kind of share are we talking?
over a 38% share. This is largely due to the sheer versatility of CPUs and their cost-effectiveness for a lot of general-purpose applications that don't need that bleeding-edge AI inference performance.
But the future is definitively specialized. That's the clear trend. It's driven by chips like application-specific integrated circuits, or ASICs, and field-programmable gate arrays, FPGAs.
Processors designed specifically to do one thing really, really well: run inference models efficiently. And the race to design the best consumer and enterprise edge devices is just ferocious right now.
Let's start on the consumer side, where Apple seems to be setting a blistering pace with its next-generation architecture. Their launch schedule for late 2025 is setting a new bar with the M5 chip.
The M5, built using third-generation 3-nanometer technology. And the source material highlights this not just as a simple upgrade, but as the next big leap in AI performance.
Okay, so what is the actual technical leap in this architecture? And why is that 3-nanometer process relevant to the user?
The architecture itself is radical. So the M5 introduces a next-generation 10-core GPU. The key innovation is a neural accelerator that's embedded in each individual core.
So they're not tacking on a separate AI chip, they're distributing the AI acceleration throughout the GPU itself.
Exactly. This makes simultaneous complex on-device computation feasible in a way it wasn't before. And this architectural change allows the M5 to achieve over 4 times the peak GPU compute performance for AI compared to its predecessor, the M4.
4 times the performance on device. What does that actually translate to for me as a user?
It means on-device, large language models, LLMs, running at much faster speeds. It means significantly improved video editing performance using AI-based tools, instantaneous application of advanced image filters. Things that used to require a trip to the cloud can now happen instantly on your machine.
And the 3-nanometer part.
That's about the physics. The 3-nanometer process technology just means the transistors are packed much, much tighter. This provides the necessary energy density to deliver that immense performance while keeping power consumption low. It's the classic Apple advantage.
And this kind of power will drive the next generation of MacBook Pros, iPad Pros, and you have to assume future iterations of the Apple Vision Pro headset.
Absolutely. That device in particular needs massive on-device compute with low power draw.
Meanwhile, Intel is battling it out on the PC side, focusing heavily on the integration of the neural processing unit, the NPU. We saw major announcements at CES 2025 about their Core Ultra Series 2.
Correct. Intel is really prioritizing AI performance for the business and enterprise edge. They're trying to make the AI PC a standard requirement, not a luxury. Their new Core Ultra 9 processors are showing tremendous generational performance improvements in AI workloads.
What kind of improvements?
We're talking about advancements of up to 3.3 times higher performance in running Llama 3 8B tasks compared to the previous generation chip.
Okay, why is Llama 3.8b a relevant benchmark here? Why does that specific model matter?
Because it's a very popular, powerful, open-source, large language model that can run efficiently on consumer hardware. So benchmarking against it shows that these new NPUs are not just theoretical. They are delivering concrete, measurable performance gains for common generative AI tasks you might actually use.
So it means a user can run significant LLM workloads locally on their laptop without ever touching the cloud.
That's the goal. It signals that this hybrid AI with local NPU acceleration is rapidly becoming the essential standard feature in the mobile computing stack.
And the Android mobile chipset rivalry is just as intense. MediaTek is pushing hard, especially on efficiency.
They are. MediaTek's Dimensity 9500, launched in September 2025, is positioned as a direct rival to Qualcomm's Snapdragon 8 Elite Gen 5 in that flagship phone market.
And their angle is power consumption.
Exactly. MediaTek is driving momentum by focusing heavily on efficiency alongside performance. The Dimensity 9500 achieves up to a 55% reduction in peak power consumption compared to its predecessor.
55%, that's a huge efficiency gain.
It's vital for maximizing the battery life of the next generation of powerful Android phones. It allows them to sustain high-performance AI tasks for much longer without draining your battery in an hour.
Okay, let's move out of the consumer sphere and into the industrial and robotics powerhouse that is NVIDIA. They are pushing performance boundaries in a way that is almost unbelievable for the industrial edge.
We have to talk about the NVIDIA Jetson Thor module, which launched in August 2025. It's marketed as the ultimate platform for physical AI and robotics, and frankly, the specifications reflect that ambition.
Give us the headline number.
It delivers up to 2,070 FP4 TFLOPS of AI compute.
Okay, let's break that down. 2,070 trillion operations per second, operating at 4-bit precision. That is a truly staggering amount of localized power. What is FP4 precision, and why is that important for something like a humanoid robot?
So FP4, or 4-bit floating point, is a very, very low level of numerical precision, and it's important because it allows the chip to squeeze dramatically more computation into the same energy envelope.
You're trading precision for speed.
You're trading a minuscule amount of mathematical accuracy for an immense gain in speed and efficiency. In industrial applications like robotics and autonomous driving, that's a trade you make all day long for perception and inference tasks, like identifying an object or predicting a trajectory.
And this performance translates to what compared to the last generation?
An astonishing 7.5 times higher performance than its predecessor, the AGX Orin, while achieving a 3.5 times better energy efficiency. It's a massive leap.
So the target market for this level of compute is clear. Advanced autonomous vehicles and that emerging, frankly, explosive field of humanoid robotics, which is driving major demand in 2025.
And NVIDIA is smart about this. These aren't just chips they're selling. They are engineered as production-ready systems designed for safety. They provide the IGX Thor platform, which are industrial-grade systems.
What does that mean, industrial grade?
It means they include crucial features like functional and AI safety through a system they call NVIDIA Halos, along with comprehensive enterprise support. This is necessary because these systems are operating heavy machinery and making real-time, life-or-death decisions in regulated industrial environments. You can't just sell them a chip and walk away.
But not every device has the power budget or the physical space for a beast like the Jetson Thor. We need to discuss the other end of the spectrum, the ultra-low power frontier, the world of tiny ML.
Yes, tiny ML, where constraints are the defining characteristic. This is all about deploying machine learning on highly constrained devices like microcontrollers, the tiny chips that power small sensors and wearables.
We're talking about systems with memory measured in kilobytes, not gigabytes.
Exactly. Maybe tens or hundreds of kilobytes of memory, often running on a small coin cell battery. The direct deployment of a conventional deep learning model on these microcontrollers is just physically impractical due to their massive footprint.
So how do engineers shrink those large, computationally expensive models down to fit into something so tiny while still retaining enough accuracy to be useful?
They use a set of really sophisticated model optimization techniques. The two primary methods are called quantization and pruning. I think the best analogy is managing digital image files.
Okay, I like that. So using that analogy, how does quantization work?
Quantization is comparable to reducing a high-resolution raw image file to a highly compressed, low-resolution JPEG. It reduces the numerical precision of the model's weights and activations.
So instead of a very detailed number, you use a simpler one.
Exactly. You reduce the precision from, say, 32-bit floating point down to 8-bit integers. This significantly shrinks the memory usage and boosts computational efficiency. You lose a little bit of fidelity, just like in a JPEG, but you retain the core meaning and reduce the file size dramatically. And the math is much simpler and faster for a tiny processor to handle.
Okay, and what about pruning? How does that fit into the strategy?
Pruning is about removing redundancy.
Yeah.
So you think of a large neural network as a complex highway map. Pruning is like systematically cutting out the less used roads or connections, the weights that contribute minimally to the final prediction.
You're trimming the fat.
You're trimming the fat. By eliminating these non-essential elements, you shrink the overall size and complexity of the model without critically harming its ability to make a good inference. And the results of combining these methods are stunning. Our sources show techniques like pruning combined with 8-bit integer quantization have successfully reduced the size of a complex model like MobileNet by 77.01%. 77% smaller. That's the difference between a model that runs for a few seconds on a small battery and one that can run for months.
It's a game changer for the IoT world. And to make this possible on the hardware side, companies like Ambiq are absolutely critical.
What's their focus?
Ambiq's entire focus is on ultra-low power semiconductor solutions for edge AI. They're critical for remote patient monitoring, body-worn devices, wearables. Their Apollo 510 MCU has this groundbreaking 10x efficiency advantage.
Which means?
It means it delivers up to 90% energy savings compared to similar technologies. This is what makes complex continuous tasks like ECG monitoring viable on a small wearable without you having to recharge it 3 times a day.
And looking even further out, we have these brain-inspired architectures that are trying to eliminate the distance between processing and memory entirely.
Yes, neuromorphic computing is finally moving toward the edge. This field tries to mimic the brain's integrated memory and processing functions. So computation isn't shuttled back and forth across a bus, which wastes time and energy. The processing happens where the data is stored.
In essence, yes. Chips like the NeuRAM, which was introduced in a Nature study back in 2022, feature an analog computing architecture that is twice as energy efficient as the existing state-of-the-art compute in memory chips. These technologies are crucial for making sophisticated cognitive tasks, which currently require large servers, viable on the smallest, most energy-constrained edge devices of the future. So let's shift from the hardware specs to the immediate value this localized intelligence is creating across crucial sectors right now. In 2024, the manufacturing segment held a dominant market position for these edge AI accelerators.
It makes perfect sense. They captured more than 22% of the entire market share.
And it's because industrial IoT systems generate these phenomenal amounts of data that demand immediate action. Our sources highlight that a single smart factory can generate over 5 petabytes of data in 1 week.
5 petabytes. Waiting for that raw data to travel to the cloud for analysis and back is just not an option when millions of dollars in production are on the line every hour.
It's not, and the killer application here, the one driving massive investment, is predictive maintenance.
How does that work in practice?
So edge AI systems continuously analyze local data in real time. Things like high-frequency vibration and temperature readings from specific components, like the bearing wear in a high-speed machine. They're listening for the earliest signs of failure.
And this real-time detection leads to what kind of improvement?
A reported 50% reduction in unexpected downtime. That's huge. This prevents catastrophic, expensive machine failures and immediately shifts the entire factory operation from a reactive maintenance model to a proactive, scheduled planning model.
And robotics in the factory are also moving beyond just simple, repetitive tasks.
They are. They're moving toward genuine collaboration. Edge AI powers what are called collaborative robots, or cobots, for much more advanced tasks like vision-guided assembly.
Because the processing is local.
The computer vision is local and instantaneous. This allows the cobot to adjust its grip strength and trajectory mid-task to handle variations in components. For example, if a part is slightly misaligned or irregularly shaped, this sub-millimeter precision enables far more flexible automation right alongside human workers.
Okay, next up, let's talk about healthcare and personalized care. This is a field that is shifting dramatically from reactive, hospital-centric treatment to something that's preventative and decentralized.
The ability to monitor patients continuously outside of a clinic is the holy grail here, and Edge AI is the critical enabler. Take remote patient monitoring, or RPM.
Right.
Devices using those ultra-low-power chips we just discussed, like Ambix MCUs, can continuously track vitals, heart rate, oxygen levels, body temperature. The continuous nature of that data allows for pattern recognition that a sporadic doctor's visit simply cannot capture.
And the privacy implications here must be a major factor in patient adoption. These edge systems handle that elegantly.
Oh, absolutely. Privacy is paramount in healthcare. One really neat innovation cited in the sources is the use of millimeter wave radar in some of these home monitoring systems.
So it's not a camera.
Exactly. This technology allows a device to detect subtle changes in breathing, movement, even falls and heart rates without capturing any sensitive visual information. It's a massive privacy win.
And this also enables rapid predictive diagnostics.
It does. Models trained on this continuous real-time sensor data can detect the early indicators of serious, rapidly progressing conditions like sepsis up to 6 hours earlier than traditional manual methods.
6 hours.
That 6-hour window can be the difference between life and death. It allows clinicians to intervene much, much earlier and dramatically improve patient outcomes.
Moving to the consumer experience, Edge AI is fundamentally changing retail, eliminating perhaps the single biggest source of friction for all of us: waiting in line.
The Amazon Go Just Walkout system is the premier case study here. And this system relies entirely on edge computing to process what's called multimodal AI locally.
What does multimodal mean in this context?
It means it's fusing input from multiple different systems at once. So you have multi-view cameras all over the store. You have sophisticated load cell sensors under the shelves that can register tiny changes in weight
So it knows when you pick something up.
instantly. And it fuses that with 3D maps of the store. So the system knows exactly who you are, what item you took, and can bill you instantly without any centralized processing bottleneck.
And this reduces checkout times by how much?
By up to 30% on average. And beyond just the efficiency, Edge AI is powering customer personalization. Retailers are analyzing in-store movement patterns, often using privacy-preserving LiDAR sensors to deliver hyper-targeted promotions instantly to a customer who might be lingering in a specific aisle.
It's a form of real-time, localized advertising that avoids the privacy pitfalls of tracking you once you leave the store.
Exactly.
Finally, let's explore smart systems in transportation and agriculture, two fields that rely entirely on navigating the physical world in real time. Let's start with vehicles.
Autonomous transportation is a pure Edge AI play. It has to be. These vehicles process millions of data points every second, from LiDAR, radar, cameras, all to build this 360-degree awareness of their surroundings.
They absolutely cannot wait for central server to tell them what to do.
No way. And the introduction of vehicle to everything, or V2X communication, further enhances this local intelligence.
Can you explain V2X in a real-world scenario?
Sure. V2X allows the autonomous system to communicate not just with other vehicles, but with smart city infrastructure. For instance, a traffic light could broadcast its current status and its predicted change time.
So the car knows the light is about to turn red before it can even see it.
Exactly. Or an emergency vehicle still miles away could broadcast its approach and its intended trajectory, allowing all the surrounding autonomous cars to make informed, coordinated decisions to clear a path far in advance of what a human eye or even a local sensor could detect.
And the military application here is a very clear demonstration of the critical need for uncompromised local autonomy.
Absolutely. The U.S. Navy is developing what they call drone wingmen, unmanned aerial vehicles that use embedded AI to carry out complex missions alongside crewed aircraft.
So the AI is on the drone itself.
It's embedded directly into the platform. This ensures these systems maintain full capability and performance even when communication links are degraded, jammed, or just completely unavailable in a contested environment. They can adapt to dynamic battlefield conditions without relying on central command.
A perfect example of decentralized intelligence making critical decisions.
It is, and that same intelligence is now reaching the farm field, leading to precision agriculture.
This is all about hyper-localized resource management.
Maximizing yield while minimizing environmental impact. Edge AI analyzes local data soil conditions from sensors, weather reports, high-resolution drone imagery to provide targeted millimeter-accurate care.
How accurate can it be?
By analyzing that drone imagery, AI models can achieve up to 95% accuracy in distinguishing crops from weeds.
Which means
It enables targeted herbicide application. Just a tiny drop on the weed, not a blanket spray over the whole field. This precision leads to a remarkable 30% reduction in water use and a 20% reduction in chemical inputs, making farming both more profitable and significantly more regenerative.
So we have established that intelligence is decentralized and embedded in our world through this highly efficient hardware. But to seamlessly connect these tens of billions of intelligent nodes, we need a massive upgrade, both conceptual and physical, to the underlying infrastructure. And that brings us to the vision for 6G.
That's right. If 5G was the network of speed and capacity, 6G is fundamentally different. It is being designed from the ground up to be AI native.
What does AI native actually mean in this context?
It means it prioritizes cognition, context awareness, and intent recognition over just raw throughput and low latency. And this is achieved by the confluence of core enabling technologies like edge intelligence, reconfigurable intelligent surfaces, or RIS, and the major game changer, semantic communications.
That concept of reconfigurable intelligent surfaces, RIS, sounds like something out of science fiction. How do these programmable wireless environments work?
They are pretty wild. RIS are essentially programmable physical surfaces. They might look like large panels on a building or even a special kind of paint, and they act as smart mirrors for radio waves.
So they're not just passive reflectors.
Not at all. Unlike a traditional antenna that just broadcasts in all directions, an RIS can dynamically change the way it reflects, refracts, or even absorbs radio signals. This allows the network environment itself to optimize the signal paths.
It can focus the wireless energy.
Precisely where it's needed. It can bypass obstructions and minimize interference. It's a radical departure because the environment is no longer a passive obstacle. It's an active, intelligent part of the network optimization itself.
And then we have the even more radical conceptual shift, semantic communication. This really feels like the biggest conceptual hurdle in understanding 6G efficiency.
It is the fundamental shift. It's moving beyond the framework that has governed all communications for nearly a century. So traditional network communication, based on the Shannon model, focuses entirely on minimizing the bit error rate, the BER.
It just tries to transmit every single bit of data as accurately as possible, regardless of what that data actually means.
Exactly. So if you send a high-resolution video of a flock of birds, the Shannon model's only job is to ensure every single pixel is delivered perfectly.
Semantic communication flips that.
It flips the entire efficiency model on its head. It aims to minimize transmission overhead by communicating content based on its meaning or its intent, rather than just the raw data.
So the network decides if a piece of information is relevant context before wasting bandwidth transmitting every single detail.
Precisely. A semantic encoder, using advanced machine learning, compresses the source message by extracting its underlying meaning. Then a semantic decoder, on the other end, reconstructs the intended message using shared knowledge and context. The goal is to infer the sender's intent with the absolute minimum transmission volume.
This seems crucial for those power-constrained edge devices and massive IoT networks where bandwidth is a primary bottleneck.
It's the only way to make them work at that scale.
And this requires completely new metrics to measure success. We have to move beyond just simple speed or accuracy metrics like BER.
We do, and new metrics have been proposed to quantify this shift toward meaning. One is called semantic efficiency, or SE. It measures the amount of meaningful information transmitted per unit of bandwidth and time.
And the other.
Perhaps most critically, semantic fidelity, or SF. This assesses how accurately the meaning that has been reconstructed on the other end matches the original intent, rather than just the bit-by-bit accuracy. These semantic-centric metrics are necessary to enable the goal-driven communication that will define 6G.
Okay, now let's address the necessary reality check. Security and the expanded attack surface. If the entire network relies on intelligence and context, how in the world do we secure a system where the intelligence itself is a potential target?
That's the core vulnerability of the intelligent network. The attack surface expands significantly because attackers no longer have to just compromise the encryption of the data. They can compromise the intelligence that guides the communication and the decision-making. We're seeing whole new threat models designed specifically to confuse distributed AI.
What are these new threats? What do they look like?
We talk about adversarial attacks and model poisoning. In an adversarial attack, malicious actors introduce subtly perturbed inputs to fool the semantic inference mechanisms at the edge.
So, tricking the AI.
Exactly. Imagine a self-driving car's AI being convinced that a stop sign is actually a speed limit sign because of a tiny, almost invisible sticker placed on it. That's an adversarial attack.
And model poisoning?
Model poisoning targets the training data itself. If a model is continually learning from its environment, malicious actors can inject misleading semantic cues or corrupted data during that training phase to slowly corrupt the decision-making of the resulting edge model over time.
And the hardware, the RIS, introduces new vulnerabilities too.
It does. It introduces physical layer vulnerabilities like the possibility of malicious reprogramming to redirect or eavesdrop on sensitive signals.
And the decentralized nature of the edge also creates major risks for these privacy-preserving AI frameworks like federated learning.
Absolutely. While federated learning, or FL, is crucial for privacy, it allows model training directly on billions of devices without centralizing the raw data. It broadens the exposure to sophisticated network attacks.
How so?
Well, FL is vulnerable to things like inference leakage, where attackers try to deduce sensitive user data just from the shared model updates, and also Sybil attacks, where numerous compromised nodes within the cooperative training environment attempt to flood and corrupt the global model with bad data.
So what are the countermeasures being developed? How do we build trust in this vast decentralized system?
It has to be a multi-layered security approach, and it demands a new trust paradigm. Blockchain technology, when it's combined with zero-trust security architectures, offers a crucial layer of defense.
Zero trust meaning you don't trust anything by default.
Nothing. Every node, whether it's internal or external, must constantly verify its identity and authority before it's allowed to interact. And blockchain, meanwhile, provides verifiable provenance for the semantic encoders and immutable logs for the edge model updates. This helps ensure that the data fed into the AI and the model updates themselves are trustworthy and traceable.
Let's end by tackling what might be the most challenging policy question here, the accountability challenge. When the AI makes a mistake autonomously, who is responsible? This is legally murky territory that has to be solved for mass adoption.
It is the most complex governance challenge we face with this technology. When an edge AI system makes an autonomous decision that causes harm, whether it's a failure in a factory cobot that injures a worker or a decision in an autonomous vehicle that leads to an accident, the accountability chain is incredibly murky.
Who do you blame? The model developer who created the initial algorithm, the device manufacturer who implemented the chip,
The system integrator who connected it to the legacy infrastructure, or the end-user organization who deployed it? It's a huge problem.
and this issue is moving much faster than our legal frameworks can adapt.
It is, but regulators are starting to impose mandatory standards. For example, the European Union's Cyber Resilience Act, the CRA, is beginning to impose mandatory requirements for secure lifecycle management and vulnerability handling across all connected devices.
So it's forcing the entire supply chain to bake in security and clear accountability from the very beginning.
From the initial hardware design all the way up through deployment and maintenance, the industry needs governance frameworks that recognize decentralized AI as its own unique paradigm, completely distinct from centralized software liability.
This deep dive has really shown us that the future of computing isn't remote anymore. It's immediate, it's personal, and it's utterly decentralized.
Right. Intelligence is no longer something we wait for from the cloud. It is truly embedded, it's customized to the constraints of the physical world, and it's governed by the laws of physics and power efficiency.
We covered the explosive scale, driven by a global AI market forecasted to hit $407 billion in 2025.
And supported by over 27 billion connected devices, a scale that necessitated the shift to the edge simply to manage the physics of latency and cost.
And we saw how specialized silicon is making all of this possible. From Apple's M5 chip, delivering 4 times the AI performance in its GPU for consumer use.
To NVIDIA's industrial powerhouse, the Jetson Thor, hitting 2070 TFLOPS to power the humanoid robotics revolution.
And we also look at those necessary trade-offs in TinyML, using techniques like quantization to deliver 90% energy savings on the smallest devices.
And looking forward, the infrastructure itself is evolving to match. 6G is moving beyond basic throughput metrics to integrate meaning and intent through semantic communication, which fundamentally changes how networks operate.
But with that autonomy comes a massive governance challenge. It's centered on security, accountability, and the necessary adoption of zero-trust models to protect against these new, sophisticated adversarial attacks.
That's the landscape.
Building on that challenge of privacy and accountability at the edge, consider this for a final provocative thought. If federated learning enables model training across distributed devices without sharing that raw, sensitive user data, we're creating a world where AI agents can become proprietary experts based on invisible datasets.
Right.
AI to AI negotiation systems are already being piloted in fields like logistics and finance. If the negotiating agents never fully disclose their underlying privacy-protected datasets, how might the very nature of business transactions change? What does true trust or even genuine competition look like between powerful, invisible, proprietary on-device AI agents?